This is part 2 of the lecture on Doppler shift. I'm also going to cover Mach numbers. Make sure that you look at the screencast regarding Mach numbers before you view that portion of today's lecture. At any rate, here's where I was at the end of part 1. I had derived for us the following expression that describes the Doppler shift in frequency. This expression takes into account in one dimensions all possible cases where you have a source and an observer. The source and or the observer can be moving. All right, so at this point, go ahead and copy down the first problem from the lecture examples. I have it here on my screen. I'm going to go ahead and read it. A car moving at 10 meters per second has a siren that emits a frequency of 600 hertz. An observer is running at a speed of 2 meters per second. Describe the 4 possible frequencies that are heard by the observer. I'm going to take a look at the first 2 possibilities, which are the easiest first. And those are what happens if the source and the observer are doing this, and then secondly, what happens if the source and the observer are doing this. Afterwards, if the source and the observer are going like so, and then like so, as we'll see, they're not quite the same thing. Well, let's take a look at the first of the 4. Okay, so let's say right here is the source, so I'm going to have the source move towards the observer first. All right, so here's the source like so, with a Vs, that's the speed of the car, that's 10 meters per second. Okay, the frequency that's emitted here by the siren itself is 600 hertz, and the speed of sound, of course, throughout all of this is 343 meters per second. Then we have the observer, like so, moving in this direction, with a VO of 2 meters per second. And now what we have to do is we just have to use the expression. When you use the expression, remember the following. The top symbol means towards. Don't look at the actual numbers themselves, just look at the directions. And then you do the numerator first, and then the denominator second. So for example, for the numerator, we have the observer moving towards the source. Therefore, we use the top symbol in the numerator, which is the plus sign. Like so. Okay, and then in the denominator of the expression, we have the source moving towards the observer. So we use the top symbol in the denominator, which is the minus sign. Like so, and now we just plug in. All right, so when we plug in, you plug in the speeds as positive numbers. All the directions are taken care of in the original derivation of the expression anyway. So in the numerator of the expression, we have 343 plus 2, so 345. And then divided by 343 minus 10, or 333 in the denominator, and then multiply that by 600 hertz. This comes out to be about 621.6 hertz. Okay, and then secondly, the next easiest situation to look at is what happens if the source and the observer are doing like so. So let's call this B. So here's the source going like so at 10 meters per second. Here's the observer going like so at 2 meters per second. And now we just set up our expression. All right, so take a look at the numerator first. In this case, pretty obviously, the observer is moving away from the source. So then therefore, you use the bottom symbol in the numerator, which is the negative sign. Okay, then down in the denominator, also pretty obviously, the source is moving away from the observer. So then therefore, we use the bottom symbol in the denominator, which is the plus sign. Like so. And now we just plug in. All right, so in the numerator of the expression, 343 minus 2, so 341. And then divided by 343 plus 10, so divided by 353. Multiply that by 600 hertz. And it comes out to be 579.6 hertz, like so. So these first 2 scenarios here, parts A and B, are quite easy to set up and evaluate. Okay, and then the next 2, what happens if the source and the observer are doing like so, and then like so is not quite the same thing, as you'll see. So let me go ahead and do some erasing here. Okay, so now for part C, let's set up the following. Let's say that the source is going like so, with Vs of 10 meters per second. And then the observer is going like so, at 2 meters per second. Okay, just qualitatively, let's get an understanding as to what should the observer hear. That is a frequency that is higher or lower pitched than 600 hertz. Well, think of it this way. Think of the marker, for example, as the source, and I'm the observer. And basically what's happening here is that the marker is catching up with me like so as we do this. So then therefore I should hear a higher pitched frequency than 600 hertz. Let's see if I do. Now when you set up the expression, ignore the numbers themselves. Just look at the directions. So then therefore, in the numerator of the expression, we have the observer moving away from the source. I mean, yes, the source is catching up to the observer, but the observer is running away from the source. So then therefore we use the bottom symbol in the denominator for that, or in the numerator, excuse me, for that reason, and that's the negative sign. So, okay, and then when we get to the source in the denominator, the source is moving towards the observer, so then therefore we use the top symbol in the denominator, which is the minus sign. Like so, and now we plug in. So in the numerator, 343 minus 2, so 341. And then divided by in the denominator, 343 minus 10, so divided by 333. Multiply that by 600 hertz, and sure enough, it's higher pitched than 600 hertz. In this case, it's 614.4 hertz. Like so. Okay, and then lastly here, what we'll call part D. As we'll see, it's not the same thing. So we have the observer now going like so, at 2 meters per second. And then here's the source going like so, at 10 meters per second. And then qualitatively, the following basically is happening. Once again, think of the marker here as the source, and then therefore the source is basically outpacing me like so as we go like this. So then therefore, I should hear something that is lower pitched than 600 hertz. Let's see what happens. All right, so let's go ahead and set up our expression. First of all, in the numerator, once again, don't pay attention to the numbers here, just look at the directions. Okay, the source is, or excuse me, the observer is moving towards the source. So then therefore, we use the top symbol in the numerator, which is the plus sign. Okay, then in the denominator of the expression, okay, the source is moving away from the observer, so then therefore we use the bottom symbol in the denominator, which is the plus sign. Like so, and now we just fill in. So the numerator is 343 plus 2, so 345, and then divided by 343 plus 10, so divided by 353, multiply that by 600 hertz, and it ends up being 586.4 hertz. So sure enough, it's lower pitched, okay? So this example here very nicely illustrates then the 4 possibilities that could occur here in 1 dimensions if both the observer and the source are moving. Okay, next I'm going to go ahead and take a look at problem number 2 in just a moment, but before I do, let me set it up for you. Problem number 2 is a nice application of Doppler shift, and that's what's referred to as echolocation. Okay, let me give you a couple of examples of echolocation that occur in the animal kingdom. For example, with bats. Bats by far have the most highly developed sense of echolocation. Now, bats can see, but they usually are nocturnal and live in dark environments like caves and so on and so forth. So their eyesight is not very good. So to compensate for this, they have developed this very highly developed sense of echolocation. Essentially what the bat does is it then essentially whistles with its own voice, and then that sound wave that it emits then propagates outwards. And then it reflects off of objects around them. So imagine a bat, for example, is flying in a really dark cave and there's no light whatsoever. So it basically whistles and emits a sound wave with its own voice, and that whistle then essentially gets Doppler shifted off of all of the objects that are in the room around it, in the cave around it. So then what the bat does is it listens to all of those Doppler shifted frequencies, and then from there it can form a mental picture of what the environment looks like around it. The truly remarkable thing about this is that as the bat is doing this, it's doing it in 3 dimensions. It's flying in 3 dimensions, and then those sound waves are at different Doppler shifted frequencies off of objects around them in 3 dimensions. And the whole time that the bat is doing this, it might be changing speed and direction as it flies through the room, and tens of thousands of other bats are doing the exact same thing. Yet the bat is able to take all of that Doppler shifted information, all of those Doppler shifted frequencies, and then turn it into a mental picture of what the world looks like around it. There are some other examples of how this occurs in the animal kingdom. Cetacean mammals, for example, are able to echolocate as well. Dolphins and whales. Okay, dolphins and whales can see pretty well, but electromagnetic radiation, light, is absorbed very quickly by water. So even in the clearest possible water, at the most, you're only going to be able to see maybe a few hundred feet, and that's it. So then therefore, those animals are able to echolocate in order to essentially learn what the environment looks like around them beyond the point which they can't see. Echolocation has been documented in human beings as well, human beings that have been blind since birth. Some people have been able to develop a sense of echolocation in quiet environments by whistling and then listening to the Doppler shifted reflection off of objects around them. So this has been documented in human beings in some cases. A technological application of echolocation is sonar technology, for example. So imagine submarine warfare. With submarine warfare, because electromagnetic radiation is absorbed very quickly by water, the best way to conduct submarine warfare and know where everybody else is around you is to instead use sound waves. There are two types of sonar. There is, first of all, what is referred to as passive sonar. Passive sonar is where the submarine basically just sits there in the water as quietly as possible, and then with very sensitive microphones, I'm sure all this information is very highly classified, what that submarine then does is it just listens to all of the sounds around it. It can then locate, for example, other submarines or boats nearby by listening to the sounds that they make. From what I've heard, sonar these days is so good that a submarine using passive sonar is able to hear somebody dropping a wrench on a boat 50 to 100 miles away. That's how good the passive sonar is. And then there's also what is called active sonar. This is that ponging sound that you see, for example, and hear in various submarine warfare movies. Let's say that you want to know where everybody else is around you, yet everybody else is staying very quiet. Well, what you then do by using a loudspeaker mounted on the submarine is you basically make a really loud sound, which then goes out and then reflects off of all the objects around you. Of course, the disadvantage to doing this is that when you do use active sonar, as it's called, this then reveals your location to everybody else. At any rate, however, let's take a look at a problem involving bats with echolocation. That's problem number 2. Go ahead and copy it down right now. Okay, so here's essentially a nice application of how bats see the world. So a bat is flying towards a wall at 5 meters per second. Okay, the bat emits a sound of 40,000 hertz, which is in the ultrasonic range of the audio spectrum. What sound is heard by the bat reflected off the wall? Once again, this is an example of echolocation. I like to break this problem up into 2 parts. You could actually do it in one shot with the expression itself, but it's a little bit easier to interpret if you break the problem up into 2 parts instead. So here's what we're going to do. Okay, first of all, I'm going to think of the bat here as a source that is moving in this direction at 5 meters per second. It emits a frequency of 40,000 hertz. And the speed of sound, once again, is 343 meters per second. And then in front of it is the wall, for example, in the cave. Think of the wall as an observer. So what I want to calculate is essentially what frequency reaches the wall. The reason why I do this is because that frequency is then reflected off of the wall back to the bat, and then the second portion of the process will then think of the bat as an observer. So then therefore I break this problem up into 2 parts for that reason. All right, so if I think of the wall here as an observer, this then means, of course, that the speed of the wall, the speed of the observer, is equal to 0. And now we just go ahead and fill in our expression. All right, so to find the Doppler shifted frequency that hits the wall, take a look at the numerator first. Okay, VO is equal to 0, like so. And then in the denominator of the expression, the source is moving towards the observer. So then therefore we use the top symbol in the denominator, which is the minus sign. Like so. And now we just go ahead and plug in. Once again, this is the frequency that will reflect off the wall. And then in part 2, we'll think of the wall as a source. All right, so 343, and then divided by 343 minus 5, so 338. And then multiply it by 40,000 hertz. Okay, so 40,000, 591.7 hertz or so. This is the frequency that then reflects off the wall. So now in the second part, we think of the wall as a source, where this is the frequency that is coming off the wall. All right, so now we think of the bat as an observer, moving in this direction at 5 meters per second. Okay, here's the wall, which we now think of as the source of this sound, 40,591.7 hertz. And then we once again use our expression. All right, so the frequency that's ultimately then heard by the bat is going to be the following. Okay, in the numerator of the expression here, the observer is moving towards the source, so we use the top symbol, which is the plus sign in the numerator. Okay, the wall as a source, of course, is stationary. Therefore, in the denominator, we just have the speed of sound of v. And then we plug in this 40,591.7 hertz in for f, and then calculate the frequency now that is ultimately heard by the bat. Okay, so I still have the number from the top board in my calculator. Let me now go ahead and multiply by 343 plus 5, so times 348, and then divided by 343. And that works out to be 41,183.4 hertz. Keep in mind, of course, once again, that all of this is occurring in 3 dimensions around the bat. All of those different Doppler shifted frequencies are reflecting off of objects at different directions in the room. Bats changing speed and direction as it flies through the cave, for example, and tens of thousands of other bats are doing the exact same thing. Okay, at this point, go ahead and take a look at the short screencast video that I've posted for you in today's folder as well with respect to Mach numbers. Take a look specifically at that animation and that screencast that I've posted for you. Okay, now that you've done so, let me go ahead and erase the board here. Okay, so let's say that we have the plane flying faster than the speed of sound, and it creates in 3 dimensions behind it that cone-shaped wake that then looks like this. All right, so the plane is here and it emits a sound wave, which then propagates outwards like so. And then the next time that the plane emits a sound wave, it is outraced this one, like in the animation. So then therefore, the next time the plane goes beep, it's here, and then the sound wave propagates outwards from that point. Next time it goes beep, it's here, sound wave propagates outwards from that point. And then let's say that at this moment in time, the plane is here like so. So obviously I've constructed here this 3-dimensional cone-shaped wake that you saw in the animation. Okay, mathematically we describe this by setting up a right triangle. Like so, where right here is the right angle. Okay, and then we label 2 of the sides of the triangle. Okay, first of all, this side of the triangle right here. That side of the triangle is equal to the speed of sound multiplied by the time that it takes the plane to go from here to here, because that's the same as the time for that sound wave to propagate from here to here. So this right here is Vt, where V once again is the speed of sound. Okay, then we also define here the hypotenuse of the triangle. The hypotenuse of the triangle here is equal to the speed of the plane, the speed of the source, multiplied by the same time t. Like so. And then we also define this angle right here. This right here, call it theta, is referred to as the apex angle. Okay, now all that we merely do here is just write down the sine of theta. The sine of theta is equal to the opposite side divided by the hypotenuse, and of course the time t here cancels out. And so the sine of the angle is equal to v over vs. So the greater the speed of the source, the smaller the angle theta. The cone-shaped wake, if you will, tightens up when the angle is small. Okay, now we actually bother now to define the reciprocal of this quantity. This is referred to as a Mach number, referred to as m, and by definition it's equal to the speed of source divided by the speed of sound. So for example, if a plane is traveling at Mach 2, that just simply means that the speed of the plane is twice the speed of sound. Mach 3 is 3 times the speed of sound, and so on and so on. Of course, because this is a ratio of speeds, it's a dimensionless quantity. Okay, the Mach number, the speed of the source divided by the speed of sound, is also then therefore 1 over the sine of the angle. So Ernest Mach, by the way, was a German aeronautical engineer who was instrumental in the development of the first jet aircraft, and ultimately then some of the engineering that was necessary for a plane to go to speed of sound or greater dates back to his original research. So that's why it's referred to as a Mach number. Okay, I'm just going to take a look at one example here involving this triangle. As you'll see, it's very simple. Go ahead and copy the third problem down from the lecture examples. Okay, so a plane is traveling at Mach 3 at an altitude of 15,000 meters. That's roughly 60,000 feet. What is the apex angle? And then how long after the plane passes overhead will an observer on the ground hear the sonic boom? Okay, so the sonic boom is going to be heard by the observer on the ground when all of these sound waves here have constructively interfered with each other and then therefore reach the person's location. So let's say that person is right here like so, and then this distance here, the altitude that the plane is above the ground, call it h, that distance here is given to us as 15,000 meters. Okay, the Mach number itself in this example is given to us as 3. Okay, so let's go ahead and calculate the apex angle first. We'll do so by just simply using this expression here. All right, so the sine of theta is then therefore V over Vs, which is equal to 1/3 in this example. Once again, the Mach number is 3. That's the speed of the source divided by the speed of sound. So the apex angle then therefore is just the inverse sine of 1/3, and we do all of this in degree mode, by the way, on our calculator. And this comes out to be about 19.5 degrees. Simple as that. Okay, then how long after the plane passes overhead will an observer on the ground hear the sonic boom? So then therefore when the plane is here and it emitted that sound wave, in the time that it takes the plane to go from here to here, the sound wave then propagates from here to here. So then therefore the person then hears the sonic boom after this time t. So then therefore to do part B of the problem, we'll just simply write h is equal to vt, where v is the speed of sound. So just solve for the time, nothing more than that. It's 15,000 meters divided by 343 meters per second. So 15,000 divided by 343, and that comes out to be nearly 45 seconds. It's about 43.7 seconds. Like so. So almost a minute goes by before you hear the sonic boom. Now, for those of you that may have heard a sonic boom, for example, before from, say, an Air Force jet or something like that, everybody's first reaction is to look immediately for the plane. Well, if the plane is at a high altitude, as it is in this problem, frankly, don't bother looking for it because the plane is actually already long gone. That's part C of the example. So part C of the example is looking for what is called the downrange distance of the plane after or since the sonic boom was heard. So how far downrange is the plane when the sonic boom is heard? Basically what we're asked to calculate here in part C of the problem is the hypotenuse here of the triangle. So that's this distance VST. Okay, now this distance here, VST, is equal to 3 times the speed of sound times t. Because remember that the Mach number is 3, so then therefore the speed of the source is equal to 3 times the speed of sound. Okay, right here, Vt was 15,000 meters. That was the value of h from earlier. So then therefore the answer is 3 times 15,000 is 45,000 meters. Okay, that distance there is 45 kilometers. That's in the neighborhood of 20 odd miles or so. So the next time that you're out in the desert and you hear a sonic boom, frankly, don't bother looking for the plane because if it was at a high altitude, the plane is long gone. Okay, this concludes the unit on waves and sound. I will be posting then for you a little bit later on the review. The review will be due by Tuesday of next week, and on Tuesday of next week, this is also when the next exam will be administered. In addition to that, don't forget to do the last problem set here for this unit on waves and sound. That will be due on the day and time that is posted for you on Schoology. Okay, that concludes then this unit. Today's shirt was obsequiae.